Okay, so let's explore some of Newton's laws problems. We're going to start off with some simple horizontal style problems, and then we're going to work on some problems where forces or objects are traveling at angles, and that's always fun. So let's look at this picture that I drew. I have a force of 100 newtons pushing on a crate or a box or an object. The object is originally at rest, and the object is starting at position 0, and the object is 20 kilograms, and there's some friction because we know that the kinetic friction, the coefficient of kinetic friction is given. And we know we're going to be asked about what's happening after 4 seconds has passed, and perhaps even how far it went at those after those 4 seconds. So we have a lot of things that we're going to consider here. Now, one of the first things we're typically going to do with these problems is, aside from drawing a sketch, I cannot stress to you enough how drawing a sketch is important. If you cannot visualize what's going on, you're not going to be able to solve the problem. I mean, that's just the way it goes. So you have to be able to visualize it and label all the given information. If you are given a problem with a bunch of forces and masses and such, and they're asking acceleration, you have one of two things. You're going to either use, for acceleration for part A, let's do it. Either you're going to be using like one of the velocity formulas, such as this, to find information about acceleration, or you're going to use one of those, or if you're given forces and mu's and everything else, you are most likely going to explore this with summation of the forces equals ma, or summation of the forces equals 0. So, we have to ask ourselves, is this accelerating or is this in equilibrium? And we can see, because of the way it's given, that it is it's definitely accelerating. Because, heck, that's what we asked for. So let's hope that that's the case. Now, when we make that determination, of course, we have to ask ourselves, well, which direction is it accelerating? Because we do have two directions to consider, and just because it's F equals ma in one direction does not mean it's F equals ma in another direction. And so we ask ourselves, in the x direction, what's going on? Is it accelerating or not? Well, this problem is asking about the x direction. All the motion in the x direction is, I can't talk. It's asked about what's the acceleration of the object, and you're obviously pushing it sideways, so it's going to accelerate sideways. In the y direction, we can assume that it is not accelerating. So if I, take my picture here, when I push this box, or when the person pushes the box, it's going to move this way, right? It's going to move sideways. So it's going to actually accelerate sideways. What I don't want this to do is to start rising above the ground or going below the ground. Right? It's not going to do this. It's not going to do this. It's moving only sideways, accelerating sideways. It is not moving up. It is not moving down. So if that's the case, I can assume that obviously the directions in the y and the forces in the y direction are in equilibrium. Now, once I make those decisions and those statements, then I can work each of these statements and go deeper into them and find out what's going on. And in order to really do this, we really need a free body diagram. So one of the other things we really should do before we do anything is a free body diagram. So let's do that. Let's do a free body diagram. So here's our object. Our free body diagram has all the forces pointing from the dot. So this is that pushing force, F equals 100 newtons. Now, we do have Mother Earth pulling, and that's gravitation, which we can figure out. We haven't figured it out yet. We are given a mu, so there's definitely a friction. And since the friction, we're assuming, we hope it works out, that we ask about acceleration. Number one, we assume the friction is kinetic. And number two, we hope that friction arrow is smaller than the pushing arrow. Otherwise, this isn't going to accelerate. We don't know what that value is, but again, something we can figure out. And of course, we have, we should have the normal force. Now, if we do this correctly, assuming, although we do have to prove it, the normal force and the gravitation arrows should be about equal but opposite because they're assumed to be in equilibrium. So now we know that, we can analyze what's going on with these forces in our respective analysis. So we're asked about the x direction, so we might as well start there first, because why solve in the y direction if we don't have to? So in the x direction, what forces do we have? Well, we have force, friction, and the pushing force. And again, we assume positive direction in the x, positive direction in the y, being to the right and up, respectively. So we go over the forces here. Well, what forces are acting, and what directions are they acting? So we're going to force ourselves on a number line here. So we're going to use just positives and negatives as indicators for direction. Well, I have a pushing force, and that pushing force is positive. And I'm going to be obnoxious with the positive to illustrate the point. And I have a frictional force, and that friction force is minus. And of course, that's kinetic. Now, realize this is really the addition of a negative force, right? Like, that's what we know. But I'm not going to write that every time, right? If I'm going to write the addition of a negative force, I'm just going to call it a minus force, right? I'm just going to call it a negative force, because that gets a little bulky and ridiculous, doesn't it? So I'm going to get rid of this, get rid of that. Sure, I'll get rid of that too. And I'm just going to put that right back. And that's going to be equal to our mass times acceleration. Okay. So we took all of this underlined summation, and we did it. We summed the forces. We took whatever forces are acting in the x direction, and we quote unquote added them, because adding a negative is still an addition, ends up looking like a subtraction. Now we're going to continue this even further. Well, the pushing force we know that's 100, but the force friction we don't know. And so you have one of two choices. You can write this off to the side and start figuring out, like, force friction kinetic equals mu kinetic times Fn. Like, you can write that off to the side, or what I will end up typically doing a lot, and this may be confusing for some, and I'm going to be sorry but not sorry, but I'm not going to write all that off to the side. I'm just going to put it into the math. I'm going to substitute it right in. I'm just going to keep the F, and we get rid of the positive, because once I denote it, I can then see what's going on. Minus, and I'm going to take that force friction, and I'm going to substitute that right over here. Right? That's the same thing. Force of friction is equal to mu k times Fn. So I'm building this equation. Don't ask me for the equation to solve any of these problems. Don't ask me, like, Tapper, what's the equation to solve this problem? I'm going to tell you, I don't know. Because every problem is going to be different, and every problem is going to require a different build from this starting point. This is the starting point. Then you have to build your formula. For every problem, this is going to look different. Same thing in the y direction. For every problem, you have to build your y formula from the starting point and then build it down. So there is no magic bullet or one equation to solve any of these. And if you think that's going to be the case, you are most seriously incorrect. You need to think about what you're given and then apply it as you go. Every problem has its own set of formulas that need to be built. Okay, well, I have a lot of this information, so I'm going to start plugging it in. I have 100 for the force. I have minus, and mu is 0.30. Fn I don't know. Mass I do know. And A I don't know. And you're like, well, I can't solve it then because I have A and I don't have A and I don't have Fn. Well, you're right. If I don't have enough information on one side, that means I always must look to the other side. And so that's what we're going to do. We happen to know that in the y direction, the normal force, positive the minus gravity, equals, move this up here a little bit, 0. So, of course, I'm going to get rid of that positive, get rid of that. I'm going to drag all this together because the force normal minus the gravity is equal to 0. And really what that's saying, we already know, if you rearrange that algebraically, the force normal is equal to the gravity. That will not always be the case. In a couple problems, that won't be the case, and I don't want you to fall into the trap. Do not always think that the normal force and the gravity are equal, because that won't happen when I start pushing things at angles. Although some of you are going to fall into that trap, and it's going to hurt. It's going to hurt real bad. Again, I don't know the normal force, I don't know gravity, but again, off to the side, I could say, well, Fg equals m times g. I do know that. Right? I do know that. And so, you know, I could solve it off to the side and then plug it in, or I'll just kind of plug it in right here in the next line item. And that's going to be equal to 20 times 9.81. And that's going to be equal to Fn. Now, if you were really fancy, you could, well, no, I'm going to hold off on that. So once I get that known, and we'll plug that into the calculator. So 20 times 9.81, 196.2. That's newtons. And then I'm going to plug that in. So what I'm going to do is, you know, that Fn is really the red Fn that's over here in the friction. So I'll plug that in. We're going to say, whoopsie. We're going to say 100 minus 0.30 times 196.2 equals 20a. That's not a 20. That's a 20. And if I solve all this math, and I'm not going to do all the intermediate algebra steps here, and subtract it from 100. And divide it by 20. 2.06. And that's technically positive. So this thing is being pushed to the right with an acceleration of 2.06 meters per second squared. And that is just the answer to part A.